called me to set you up. Want me to come and wet you up. Cause you a out of town nigga like Biggie. Heard about the shit with Diddy, so I came through to vest you up. And I got a vest for 40, a vest for...
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA. And today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we're going to incorporate what we learned before in thermodynamics to what we're learning currently in electrochemistry. So we're going to relate the cell potential to electrical work and free energy. So to begin, a volt, which we're measuring with the voltmeter, is a joule of work per coulomb of charge that's being transferred via these electrons. So what we can do is write out the potential difference between these two electrodes, in this case the zinc and the copper, as being the work, or the electrical work, over charge, where the charge is the electron being transferred from one to another. And as I mentioned before, this is in joules per coulomb, where joules is the unit of work, coulomb is the unit of charge. And that's why the potential difference is measured in units of volts. So in this case, a battery or a system is doing work. So then the amount of work that leaves the system is going to be given a negative sign. And so the cell potential, which I'm going to write as E, is going to be negative work over charge. Again, this negative sign indicating that work leaves the system. So from here, we can rearrange this equation and say that the work, or the electrical work being done, is negative charge multiplied by the cell potential, E. So remember, this cell potential is the maximum potential, right? The maximum work that can be done. And so from here, we can actually write this out as the maximum work negative charge times E. So I hope you're following this step-by-step process up until now. So another unit I'm going to introduce you to is the Faraday. So Faraday is actually a constant value, but the definition of it is that it's the charge of 1 mole of electron. And the Faraday's constant is a value that is given 1F is 96,485 coulomb per mole. So charge per mole of electron. And this is a value that's given to you at the back of your textbook. On a test, it'll be provided, so you don't have to memorize this value. So from here, we can get that the charge is the moles of electrons transferred multiplied by the Faraday's constant, right? Because charge is the flow of electrons going from one electrode to another, and that's dependent on how many moles are being transferred multiplied by this constant value to make it into units of coulombs. So in this case, for example, zinc going to zinc 2+ is releasing 2 electrons. So we would have 2 electrons flowing here, 2 electrons flowing in here to make solid copper. So in this case, the moles of electrons being transferred is 2. And so this can also be written as NF, where N represents the number of moles. So we can combine these two equations together and get the maximum work being equal to negative NF, taking over the charge part, and the cell potential. So this is a very important equation to look at. And then from here, for a reaction, for example, a redox reaction in a battery, which is represented right here in this kind of setup, when it's at constant temperature and pressure, we learned in thermodynamics that the maximum work is equal to the change in the free energy, or delta G. So now we're going to relate the work to the free energy. So we can rewrite this equation as delta G equals negative NFE. And this is a really important equation that you will experience a lot when doing calculations involving cell potentials and free energy. So looking at this equation, you can tell that for a spontaneous process, remember we learned that delta G has to be negative, right? And since there's a negative sign right here, what that means is that the cell potential has to always be positive for a reaction to be spontaneous. And also for standard conditions, we can again write this same exact equation but with a naught up here and write negative NFE, standard condition, cell potential. And so the maximum cell potential is directly related to the free energy difference between reactants and products in the cell. So now let me show you an example. Here's an example problem. Will a gold ring dissolve in 1 molar nitric acid, HNO3, to form a 1 molar Au3 plus solution? So let's write out the two half reactions, right? So first step, write half reactions. So the nitrate anion can be reduced to nitric oxide. And so the first half reaction we'll write down is NO3 minus plus 4H plus 3E minus going to nitrous oxide plus 2H2O. And when we look in the reduction potential table, we find that the potential for this is going to be 0.96 volts. So this is the reduction potential found from the table at the back of your textbook or online. And then the other half reaction for gold being oxidized, but let's write it out as the reduction potential first, where we have Au3 plus 3E minus goes to Au, where the reduction potential is 1.50 volts. But since in this particular instance we're starting out with a gold ring dissolved in the nitric acid, this is going to be the equation that's switched over. And so that means this value for the reduction potential is going to be negative since this is an oxidation process. And this is the reduction. So from here we get an overall reaction of solid gold plus aqueous nitrate plus 4H plus going to Au3 plus, which is aqueous, plus nitrous oxide, which is actually a gas, plus 2H2O. And then we can calculate the potential for the whole reaction, for the redox reaction, as being 0.96 plus negative 1.5 volts, so minus 1.5 volts, which gives us negative 0.54 volts. Now, again, since I went over the units of voltage, we can actually write this out as negative 0.54 joules per coulomb as well. So now let's figure out the delta G of the redox reaction using the equation that I just showed you guys. So it's negative NFE. And so this circle tells us that it's at standard conditions. So the number of moles of electrons that are being transferred, we can see, is 3. The reason why it's not included in this overall equation is because they cancel each other out on the other side. And so we have 3 moles of electrons. The Faraday constant, which is 96,485 coulombs per mole of electron. And then we have the E naught value, which is negative 0.54 joules per coulomb. So now you can see why I converted the units right here, so I can cancel them out. We can cancel the moles of the electrons, we can cancel out the coulombs, and we end up with a value in joules, which is good since free energy has to be in joules. So we get a value of positive 1.56 times 10 to the 5 joules. So now we can see that since delta G is positive, gold would not dissolve in 1 molar nitric acid because it's not a spontaneous process. It's not going to happen. Even before we did this calculation, we could have actually been able to tell by looking at the energy, the electrical potential value, right? Because this has to always be positive for a reaction to be spontaneous, and delta G has to be negative for a reaction to be spontaneous. But here I walked you guys through both of these calculations so you can just see how it's done.